for centuries felt like staring at just an unscalable mountain. Imagine facing a mathematical problem so intricate, so huge that the idea of finding a perfect exact answer seemed, well, completely impossible. Not just hard, but fundamentally beyond our reach.
Exactly. Yeah. For a very long time, problems like this in mathematics, they were either, deemed unsolvable by the usual methods, or you only got these, frankly, frustratingly close approximations.
Yeah.
But what if? What if there was a way to actually bypass those limits?
And that's really our mission today. We're diving deep into something called Ezouidi's theorem. It's a pretty groundbreaking method that completely redefines how we solve these high degree polynomials. This isn't just tweaking things, it's a fundamental shift. It offers exact symbolic solutions for equations that have been, huge challenges. Some were even considered unsolvable by older theorems. We're talking about getting absolute precision where, frankly, precision seemed like an impossible dream.
And what's really fascinating here is how this theorem doesn't just work around long held assumptions, it actually challenges them pretty directly. So,
Mhm.
the central question we want to unravel is how on earth can we get absolutely precise, exact answers for something as, well, frankly, as daunting as an 18th degree polynomial, especially when our most established methods often just fall short or even say it's impossible?
Okay, let's unpack that a bit. First off, why are high degree polynomials such a monumental headache for mathematicians? When we say 18th degree, we mean the highest power of x is 18. That means potentially dozens of terms, this cascade of coefficients. It gets complicated fast.
But the complexity isn't just the number of terms, it's about how deeply they interact. Think about like a simple linear equation, x plus 2
Yeah.
equals 5, easy. And even a quadratic, by 2 plus 2x plus 1 equals 0, that is a straightforward formula we all learn. But as that degree climbs higher and higher, the polynomial's behavior becomes wildly unpredictable. You get multiple roots, real ones, complex ones. It's incredibly difficult to pin them down precisely.
And for ages, we've had like two main ways to try and deal with these beasts, right? And neither really gave us that perfect exact answer we were looking for. First, you've got numerical approximations, things like Newton's method, maybe.
Yes, exactly. Methods like Newton's are super useful in, say, engineering and science, but they're essentially sophisticated guessing games. They use an iterative process, step by step, to get closer and closer to a root. But, and this is the crucial bit, they only give you approximations. They always come with this risk of rounding errors, tiny errors at each step, but they can accumulate, especially in complex calculations. So they just cannot guarantee the exact value. It's like trying to pinpoint a specific atom using a really good ruler.
Yeah.
You get close, maybe very close, but never exactly there.
Okay, so approximations get you close, but not exact. And then there's classical algebra, which actually kind of put up a definitive wall for many of these problems. Which brings us to Abel's theorem.
Right. Abel's theorem, a huge deal in 19th century algebra. It established a really profound limitation. It basically states there's no general algebraic solution using radicals,
Mhm.
things like square roots, cube roots, any higher root for polynomial equations of degree 5 or higher. For centuries, this theorem just stood there like an unshakable boundary. It essentially told mathematicians, look, for many of these high degree polynomials, you just cannot find their roots using the same kind of exact radical expressions you use for quadratics. It created this whole category of problems considered algebraically unsolvable in that specific exact sense.
Wow. So for generations, we lived with this mathematical gap. For a huge chunk of these high degree polynomials, the holy grail of precise symbolic solutions was just considered fundamentally out of reach. We either had to settle for those approximations or just accept that a perfect answer in that radical form wasn't possible.
And that's precisely where Ezouidi's theorem steps in. It offers a completely new paradigm. As its developer, Mourad Sultan Ezouidi puts it, it excludes all classical methods. This isn't about finding a clever trick within the old rules, it's proposing a whole new set of rules.
That's a really bold claim. Excludes all classical methods and directly contradicts Abel's theorem's implications. How can it possibly do that? I mean, Abel's theorem has been foundational for so long. Are we talking about redefining solvable or using a completely different kind of math?
That's a really crucial point, and it's where the insight lies. Ezouidi's method isn't really defying the logic of Abel's theorem directly. It's more like it's operating on a different plane. See, Abel's theorem talks about solutions in terms of radicals applied to the polynomial's original coefficients. Ezouidi's theorem, though, uses this sophisticated recursive symbolic process. It transforms the polynomial itself, revealing a hidden structure that classical methods just weren't designed to see or use. It shows that exact roots can be found, maybe not always in the radical form Abel was talking about, but through this structured, iterative symbolic manipulation. It leads to a precise, non approximate result. It sort of bypasses the limitations of classical algebra by changing how we even represent the problem.
Ah, okay. So it's less about breaking Abel's specific rules about radicals and more about playing an entirely different, maybe more powerful game.
It's not trying to use the radical tools that Abel said wouldn't work for everything, but using a completely different kind of mathematical machinery to get the exact answer anyway. Exactly. It says, look, we can get precise, solvable roots where traditional approaches, kind of stuck with their specific tools, just failed. The promise here isn't just a slightly better approximation. It's delivering exact symbolic roots through this highly structured recursive process. It gives you the precise, definitive answer, totally free from the uncertainties of numerical methods.
To really get a feel for this breakthrough, we need to see it in action. We're not just going to talk theory. We're going to confront one of these unsolvable beasts head on. So imagine being handed this colossal 18th degree polynomial, a string of numbers and variables that would make even seasoned mathematicians sort of pause and probably reach for their approximation software. Okay, take a deep breath, because here it is, the beast we're going to try and tame today. P8x by 18 by 17 plus 153 by 16 plus 3060 by 14 plus 3060 by 14 plus 14560 by 13 plus 1560 by 13 plus 15758 by 10 by 9 plus 43758 by 10 no by 9 plus 1598346 by 5 plus 4083136 by 5 plus 12city by 4 plus 4083118 by 3 1750131 by 2 plus 437553x 2037200. I mean, just seeing that written out, it's almost overwhelming, right? All those terms, those huge coefficients, it just screams, good luck solving me exactly. It really highlights why traditional methods would struggle or just give approximations.
Indeed. That polynomial is a perfect candidate, really, to show the power of Ezouidi's theorem. Traditional methods would absolutely struggle to find anything but approximate roots for something that complex. But with this theorem, we come at it from a totally different angle, trying to leverage its intrinsic structure.
So how does it actually do that? What's the magic? How does Ezouidi's theorem tackle this monster and pull out its exact roots?
Well, the core idea is that the theorem lets us represent and then transform the polynomial in a way that sort of reveals its underlying structure, and then it solves for the roots symbolically, not numerically. It uses a recursive process, step by step, to find the exact values.
Okay, recursive symbolic process. That sounds key. Can you break that down a bit more? Like, what makes these symbolic coefficients different or more powerful than just the numbers we see in the equation?
Yeah, absolutely. Think about the number pi. Numerically, you might use 3.14159 here, right? Which is an approximation. A symbolic representation, though, treats pi itself as the exact thing, the infinite value. Ezouidi's theorem takes the original numbers in our polynomial, like that 18 or 153, and doesn't just treat them as fixed values. It builds them into new symbolic expressions. Think of them like formulas built inside other formulas. This lets us do calculations and transformations without ever losing a single decimal place, without introducing any rounding error. It keeps the absolute mathematical truth intact at every single step.
I see. That's a crucial difference. So instead of just number crunching and hoping for the best, we're building up this precise symbolic representation, almost like a mathematical code for the equation's structure. How does this recursive formula then work with these symbolic coefficients?
Precisely. At the heart of it is this unique recursive formula. Imagine like a set of precise mathematical instructions that feed back into themselves. At each step, this formula takes the polynomial's original coefficients, mixes them with symbolic terms calculated in earlier steps, and systematically transforms them. It's kind of like building a very complex structure, brick by precise mathematical brick, always maintaining those exact symbolic relationships. It refines the polynomial's form as it goes.
So it builds on itself step by step, all done symbolically. That sounds like it could be a lot of calculation, but the key is it's done with absolute precision. And this is where we get to that aha moment you mentioned for this specific polynomial.
Yes, exactly. This incredibly careful, exact calculation of coefficients is vital because it avoids any rounding errors. And what's absolutely remarkable for this specific 18th degree polynomial is the huge simplification that just emerges from this process. Ezouidi's method isn't just crunching symbols randomly, it's designed to spot and use very specific patterns, symmetries, within the polynomial's symbolic form. Think of it like a special key for a really complex lock. Other methods might try brute force or just jiggle it, but Ezouidi's finds the exact tumblers that align. It reveals the polynomial's simpler, hidden core. And this particular polynomial It turns out it has this deep hidden symmetry that the recursive process is perfectly suited to uncover.
That kind of dramatic simplification for an equation that huge sounds almost like, well, mathematical magic. What is it about the theorem's design, or maybe this polynomial's specific nature, that lets all those terms just collapse? What's the insight that traditional methods miss?
It really is a kind of dance between the theorem structure and the polynomial's own hidden structure. Through this rigorous recursive process, Ezouidi's theorem basically sifts through all the complexity, and what it finds for the specific polynomial is honestly astounding. Most of those carefully calculated symbolic coefficients actually simplify down to zero. We find 0r all the way through S7r are zero, and then S9r up through S16r are also zero. It's like the polynomial was wearing this incredibly elaborate costume, but Ezouidi's theorem stripped it right down to its essential elegant core.
Wait, really? Almost all of them vanish. For an 18th degree polynomial, that's genuinely incredible. Like finding a tiny, perfect mechanism inside a giant machine.
Precisely. For this polynomial, only two of these symbolic coefficients remain non-zero. Now, these remaining coefficients, they're still complex symbolic expressions themselves. One involves 488619, I get 189, and the other 488618, I get 205 at 18 and 18. But crucially, they are exact symbolic values, not rounded numbers. And that's the whole point. This exact symbolic calculation is critical because it preserves the integrity of the solution. No approximations, no rounding errors allowed. We aren't estimating, we're finding the precise values.
Okay, so we've gone from this absolute monster of an 18th degree equation with, what, 19 terms originally, down to something vastly, almost unbelievably simpler, all thanks to this recursive symbolic process. So how do we get the actual roots now from that much simpler form?
Well, the beauty is because almost all those symbolic terms vanished. The original polynomial simplifies dramatically. It transforms from that huge, daunting expression into just this. Px, please say 8 by 9, plus S17r equals 0, 0. It's a massive reduction in complexity.
That's a huge step. And now we can just plug those non-zero values, the symbolic ones we found, back into the simplified equation.
Correct. When we substitute the calculated symbolic values for HER and S17, our simplified polynomial looks like this. By 18 plus 48619, that was 189 by 9, plus 48618, 205, 1818 equals 0.
Okay, I'm definitely seeing a pattern here now. By 18 and by 9, that looks really familiar, doesn't it? Like something from algebra class.
It does. This is where that profound simplification really pays off. We can now recognize this as a quadratic equation, not in x directly, but in bay 9.
Yeah.
If you just think of, say, y bag 9, the equation becomes y2 at dar plus s17r equals 0. And that means we can use the good old quadratic formula directly on by 9.
Wow. So this clever simplification turned what looked like an impossible 18th degree problem into something solvable with a tool most of us learned back in high school. That's genuinely remarkable.
It really is. We can introduce an intermediate step just for clarity, maybe call it S1R, which equals S8R2 plus 4 is S17. Then applying the quadratic formula, we get the exact symbolic result for by 9. It's SAR9 as HER didn't just score it, and SS1R is 2. Now, when we substitute the full symbolic values back in, this expression for by 9 still looks complicated, sure. But the key is it's entirely exact.
Yeah, even that expression 4 by 9 looks pretty intense, but you're right. The critical thing is it's exact. No rounding, no approximations hidden away. It's the precise mathematical statement.
Absolutely. So the final step to find x itself is just to take the ninth root of that entire complex expression we just found. And so the complete root structure, we also need to incorporate the base term, which in the original polynomials setup was effectively 18. This gives us the final exact symbolic root. It can be expressed using complex exponentials, and it looks like this. X equals 18 plus 18, 3361, 26361, 2689, 219.
And just to hammer this home for you, our listener, this expression right here, that is an exact symbolic root. It's not something we're rounding off or estimating. It is the precise, definitive answer. That is truly phenomenal, especially for something that, is considered way too complex for classical methods, maybe even unsolvable in that exact sense.
That really is the core message here. Ezouidi's theorem doesn't rely on numerical approximations at any point in the process. The roots we get are exact. They aren't subject to those cumulative, error-prone calculations you get with numerical methods. This approach guarantees absolute accuracy even for polynomials that were previously thought too complex or just plain unsolvable for exact roots for the traditional needs.
So stepping back, what does this mean for the bigger picture? Why does having an exact symbolic solution matter so much? Beyond just, satisfying mathematical curiosity, are there real-world implications for this level of precision?
Well, absolutely. If you think about the broader landscape, science, engineering, the ability to get exact solutions can be transformative. Think about fields like, say, advanced physics, quantum mechanics, general relativity. They demand incredible precision. Approximation errors there could lead to completely wrong conclusions. Or think about secure cryptography. The smallest deviation could compromise everything. Exactness is absolutely paramount. Or even designing complex AI algorithms, sophisticated control systems, tiny inaccuracies can cascade and have really unpredictable effects down the line. This method offers a powerful new tool. It's a fundamental shift, really, in how we approach problems that used to trap us in this cycle of just getting close enough. It lets us truly understand the fundamental nature of these solutions rather than just estimating them. It means building our models or systems on truly unshakable mathematical foundations.
What really stands out to me is that this isn't just about solving one really tough polynomial, is it? It's about a new way of thinking, a new lens for looking at mathematics itself. We started with this incredibly daunting 18th degree polynomial, one that would make anyone pause. We talked about how traditional numerical methods could only offer approximations, always with that risk of errors, and how classical algebra, through Abel's theorem, even seemed to declare many problems like this inherently unsolvable using radicals.
And then we saw Ezouidi's theorem offer a complete redefinition. Through its structured, recursive, symbolic process, it uncovered this hidden elegance. It simplified that massive polynomial right down to its core structure, and that allowed us to derive an exact symbolic root, a precise solvable answer. You bypass those historical limitations, bypass the need for approximations. It's really a testament to the idea that sometimes what we call unsolvable just needs a different, maybe a deeper perspective.
Absolutely. It's a testament to the power of fresh thinking, of innovative mathematical frameworks that can unlock secrets we thought were locked away forever. This deep dive into Ezouidi's theorem really makes you stop and think, doesn't it? If a mathematical theorem can reevaluate and provide exact solutions for problems we've considered intractable for so long, what does that really say about the boundaries of our knowledge?
It really raises an important question, doesn't it? If Ezouidi's theorem can crack polynomials that centuries-old methods found intractable, how many other long-standing mathematical problems are out there? Problems currently deemed unsolvable or only solvable approximately. Might they also yield to entirely new, structured, maybe recursive approaches like this? It forces us to reconsider what we even mean when we label something solvable or unsolvable.
Indeed. It leaves you wondering what other deep mathematical secrets or maybe even complex real world challenges are just sitting there waiting for a different way of looking, a new framework to reveal their hidden elegance. Well, that's all for this deep dive into Ezouidi's theorem. We hope you feel a little more well informed and perhaps, yeah, a little more inspired by the possibilities of profound mathematical innovation. Until next time, keep diving deep.